Hello. Today I'll answer a fundamental question in signal processing. Is the response of a linear time invariant system to a complex exponential signal also a complex exponential? The answer is definitive true. In mathematics, we all call these signals eigenfunctions. It means they pass through the system without changing their basic form. And why? Let's look at the math on the left. The output system y of t is the convolution of the impulse response h of t and the input e to st outside of the integral. What remains inside the integral is simply a complex constant for any given frequency. We call this constant that transfer function, h of s, as the diagram on the right shows. The input e to st goes in and the output is just the same e to st, scaled by h of s. So the conclusion is true. The exponential form does not change. This is exactly what we saw in our previous task with filters. The filter didn't create new frequencies. It just used its transfer function, h of s, to change the amplitude and shift the timing of the existing signals. And the second question is the transform. I will explore in the region of convergence or ROC with defines where the transform summation actually exists. The shape of the ROC tells us exactly what kind of signal we are dealing with, whether it's causal, anti-causal, or a mixture of both. Causal and anti-causal analyze. Look at the first two diagrams. For a causal sequence, which is right side, the ROC is always the exterior of a circle, defined as z, and the defined as magnitude of z is greater than R max. This means it extends outward from the outermost pole. Conversely, for an anti-causal sequence or a left-sided signal, the ROC is the interior of a circle where magnitude of z less than R max. In this case, it shrinks inward from the innermost pole. Non-causal and stably, what if the signal is two-sided or non-causal? The ROC becomes an annular ring between two poles. R1, 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 the magnitude of z is between R1 and R2. A critical rule in DSP is that the ROC never contains a pole. Furthermore, if this ring or circle includes the unique circle, we know the system is stable. And the conclusion is, in summary, the ROC shape is not just a math property. It is the visual signature of a system's causality and stability. Understand the shape and you understand the system. And the second question is Fourier analyze frequency variables and mapping. In Fourier's analyze, we operate into parallel worlds. The continuous time domain and the discrete time domain. Understanding the variables and the unique that define these worlds is crucial for accurate signal processing. In the continuous domain, we use cycling frequency f, measured in hertz, and the angular frequency omega, capsule omega, measured in radians per second. These variables represent physical time and can range from 0 to infinity. However, once we sample a signal with the sampling frequency fs, we enter the discrete domain. Here, the variables change to discrete angular frequency small omega and normalized frequencies f. The units shift to radians per sample or cycles per sample. The fundamental bridge between these two is the sampling period Ts. The relationship is defined by the equation omega small omega equal capsule omega t of t of s. Essential discrete frequency is a normalized version of continuous frequency. Because of this scaling, the entire analog frequency spectrum is wrapped around the unique circle. A critical takeaway is that while analog frequency is infinite, digital frequency is periodic. The highest unique frequency we can represent, the Nyquist frequency, maps exactly to small omega equal pi equal tau. Any analog frequency beyond this point will result in a lysis, where the signal folds back into the native tau to tau range. This normalization allows us to analyze systems independently of the specific sampling hardware as long as we know the scaling factor Ts. And the question 4 is geometric interpretation of magnitude response. The magnitude response of an LTI system can be elegantly interpreted as a geometric problem. Under the plan, instead of just looking at algebraic equations, we can visualize how poles and zeros physically shape the frequency response that we observe in tools like the Signal Analyzer app. Look at the Z-plan diagram on the right. We have our unique circle, which represents all possible frequencies small omega as we move along its perimeter. For any specific frequency, we identify a point P at E to JW to find the magnitude H of E to JW at this frequency. We draw factors from every zero and every pole to this point P. The magnitude is simply the product of the length of the vectors starting from the zeros divided by the product of the length of the vectors starting from the poles. Mathematically, this is expressed as magnitude h of e to jw equals a constant k times the product of magnitude vzi over the product of magnitude of vpi. This gives us an immediate physical intuition. When our frequency point P moves close to a pole, the distance magnitude Vp becomes very small. Since this term is in the denominator, the overall magnitude shoots up, creating a peak in the frequency response. Conversely, when P moves close to a zero, the numerator becomes small and the magnitude dips toward zero. By simply looking at the pole zero map, we can predict where the peaks and the valleys of a filter will occur, allowing us to design complex filters by strategically placing this point on the z-plane. And the last question is block convolution. When filter extremely long sequence with an FIR filter like the one we analyze in our impulse response task, we cannot process the entire signal at once. Instead, we use block convolution methods, overlap add and overlap save. The overlap add method divides the input into non-overlapping blocks. To avoid aliasing, we append the m minus 1 and minus 1 zeros to each block, where m is the filter length. After performing convolution, each output block is longer than the input. Consequently, the tails of these blocks overlap. We finalize the output by simply summing these overlapping tails, ensuring a mathematically perfect reconstruction of the linear convolution. Alternatively, the overlap save methods use overlapping input blocks. Each block starts with the last m-1 sample of the previous block. We then perform circular convolution using FFT. However, circular convolution costs periodic aliasing at the beginning of each result. To solve this, we simply discard the first m-1 samples of every output block and save the rest. In summary, overlap add relies on linear convolution and the summation, while overlap save invariates the efficiency of circular convolution and data discarding. Both methods effectively eliminate the infinite memory requirement for long signals while maintaining the precise filter characteristics we have designed in our frequent response studies. My presentation is in the end. Thanks for your listening.